Et on va commencer. So I will switch in English now for this second session of the afternoon. And so as Soraya said in introduction, we have two highlights for this scientific days. One highlight will be on this general question, rethinking risk analysis and management. And more specifically, we will consider in a first short keynote given by Valerio Cozzani, the problematic, the issue of cascading risk. You can, if you want to sign. And in the second short talk also, we will consider infrastructure resilience. And the first talk will be given, as I said, by Valerio Cozzani. I will give a very brief introduction about Valerio. Valerio is a full professor of chemical engineering at the Università di Bologna in Italy. He is head of the Department of Civil, Chemical, Environmental and Materials Engineering. Is it right? So your research focuses on process safety, industrial risk analysis, and sustainability of chemical energy systems. You have developed a lot of innovative methodology, so we will share some aspects of them, for hazard assessment, including domino effect. So this is the question. In the context of NATEC events and other security-related risk, so you have coordinated numerous international and national research projects funded by various institutions and major industries also, and co-authored a lot of scientific publications. So I give you the floor.
Thank you.
For this first short
Thank you. And thank you to all of you. And I apologize if I cannot master French, so I will speak in English. So sorry for that. What is really important in my CV is not most the achievements, but my background, that is chemical engineering. And so I will introduce a slightly different perspective, looking at cascading events from a technological point of view, or at least looking at with a competence that is mostly focused on the last technological event of the system. First of all, I would like, in this framework, in this specific framework of the chemical and energy industry in which I work, to identify a few categories of cascading events, and then look at some factors that are actually enhancing the vulnerability of these industrial sectors to cascading events. And finally, some key elements of how we can manage the risk and prevent and reduce the risk due to this specific type of scenarios. My starting point is the anniversary that we have this year, 50 years passed since the Seveso accident. That is a kind of cornerstone event in the chemical industry, starting a number of European regulations, the so-called Seveso directives, that were effective in leading to the introduction of appropriate management systems to prevent the risk of major accidents. And we assisted in since the first Seveso directive that was issued in 1982 to a definite reduction of the number of recorded accidents and of the number of fatalities in the areas covered by this type of industry, by this directive. However, this is also the reason why we now focus on cascading events. Cascading events are complex scenarios, and from a mere point of view of probabilities, the probabilities, or if you like, the expected frequency of occurrence is lower than a simple conventional accident. But when on the side of the conventional accident you have a management system that controls and reduces the risk, this type of events come out as relevant. And unfortunately, the conventional risk management techniques established a few decades ago are not effective in managing this, the specificity of this type of scenarios. The interest in cascading events in technological systems, or at least in the chemical and energy industry, started with a cornerstone accident in 1984, the Pemex LPG accident at San Juan, the Ixapotec in Mexico, where there was a huge domino event in which, after a first fire, several other occurred, ending up in more than 500 fatalities and a huge damage in the area, the almost total destruction of the industrial facility and of the nearby residential areas. Domino events actually imply the propagation in time and space of an initial accident, so that multiple simultaneous events become possible, which is a scenario that is usually excluded when you don't have this type of cascading issues. However, when looking at domino events, the causes of domino events, so the initiating events, is still internal. First responders may immediately come into action. Utilities and safety systems are usually still available, and you don't have an overload of the emergency response. So it is, this makes the situation much more simple than in a second type or category of cascading event that, also due to climate change, is now more in the light of both research and also competent authorities dealing with the problem of accidents, of cascading events. This in particular concerns the impact of natural events, natural hazards, as earthquakes, floods, and intense winds on industrial installation and infrastructure. Obviously, when this happens, the potential release of the hazardous substances in this installation may amplify and propagate the consequences of the accident. This doesn't only concern chemical and conventional energy industry as oil and gas, but also other branches of industrial installation. And maybe here the cornerstone accident that we have is the Daiki nuclear power station accident in Fukushima in 2011. I must say that stress tests carried out in Europe, and in particular in French nuclear power stations, in France, because France is the European country that has the highest number of nuclear power station at the time, showed that that accident was possible as well in European power stations, due to the fact that a number of factors related to the impact of intense natural events, not directly on the structure of the system, but on auxiliary systems as pumps, external power station, and so on, can lead to severe accidents. And here, it is important also to remark that the trend of intense natural events recorded is increasing, and this results in an increase in the number of NATEC events, and when you go to investigate which is the natural event or the natural hazard starting the cascading event, as you can see, these are mostly natural hazards that are related to weather or to climate. And so that can, in perspective, change. Specific elements of NATEC scenarios are somehow different from the previous domino effects, and in particular, they come from causes that are external to the site, and this is a first important point. There is no knowledge inside a chemical company or inside an energy company, usually, to address this specific type of hazard. There are no specialists, while there are specialists of safety management which are perfectly aware of domino effects of conventional accidents. This is not the case when you consider natural hazards. First responders should give priority to residential areas that can be involved, can be simultaneously affected by the same natural hazard or natural event. And so you will not have an effective first response. Utilities and safety systems may be damaged as well by the natural events. And so there is the possibility that the final scenarios are significantly different from those that are expected. There is also a third type of cascading events which I would like to mention because this came out as something that was, let's say, maybe less relevant or different before the last pandemics. Since September 11, 2001, we are all aware about physical security issues that can potentially look at chemical and energy infrastructure in order to amplify the consequence of some kind of intentional misconduct. And there are plenty of examples all around the world of attacks carried out on energy infrastructures, not as a war action, but as terrorist acts. But what changed, and it changed after the pandemics, is the opening of the networks of companies to the web, to the global web. And this creates a new vulnerability to cyber security events. We had up to now an example with the Colonial Pipeline ransomware attack that was limited to somehow stop the operation of the infrastructure. But still, in theory, it's possible to go further in the sense that once you have access to the system, it is possible to access from the IT system to the operating technology, to the OT, and by changing process parameters and process variables, it's possible to cause specific accident scenarios or to damage the infrastructure. And it is important to understand that even if there are approaches for security vulnerability risk assessment, these do not provide a specific support on cyber threats and the assessment of the consequences on operating technologies. So it is important to understand that we are facing a quite complex situation with respect to these cascading events in which we have basically a vulnerable system. Vulnerable due to the increasing complexity of our supply chains, which is due to intensification, decarbonization, circular economy imperatives that are all positive processes. Still, they imply that the systems, the industrial system, become more and more complex and might need a geographical distribution that was not originally present. And also we have a further complication due to the fragmentation in industrial clusters of the industrial companies, which usually do not operate with respect to these streets all together, or at least they have a separate management between conventional accident and this type of cascading events that might not be effective. There is also a matter of increasing interconnection. There are, again, positive processes as, for example, the Verbund, the sustainability approach of some chemical companies that however makes one plant depending on another. That means if you have a disruption or a deviation, this can easily propagate in the system, or it's easy to stop or to damage the system with important times for restoring the operation. And finally, I have already mentioned the point of increasing digitalization. All this results in a potential spiral to events of unprecedented severity unless we take action by implementing specific strategies to control as well this type of risk. Obviously, there are several possibilities. I have here highlighted 4 key elements of these strategies. The identification of these hazards is extremely important. Identification brings with it awareness and allows to implement safety measures, mitigation measures, protection measures. After the identification, which is a qualitative step, a quantitative step is required, and in particular, we need to innovate the tools for risk assessment and risk management, because these are not usually adequate to cope with cascading events. And also, there is a process which is actually ongoing, where we can change our design procedures, and this is something that we are experiencing in Europe with the Eurocode approach that is changing somehow the original approach based on a deterministic identification of scenarios and events. And finally, the issue of resilience. I have now time here only to focus on one of these aspects, and I would like to stress a couple of issues concerning risk assessment and risk management. Here, when looking at cascading events, we have to cope with a dynamic assessment of the scenarios, simultaneous multiple scenarios, and scenarios that are specific of cascading events. And this is a first point requiring innovation of risk assessment techniques, which usually address specific independent events. A second point concerns safety barriers that are the main tool that we introduce to protect ourselves from the hazards. With respect to innovative methods for risk assessment and risk management. A lot of work is ongoing in the literature. However, this innovative complex method all rely at some point on the probability that an element in the system fails. And here, there is still limited work on what I have called in this slide the key enabling models for equipment damage or for the damage of the single elements of the chain. This is something that needs a specific attention because this type of damages are not the standard consequences of accidents and are somehow not usually considered. It's a kind of management models addressing exceedance of design conditions. Second point concerns safety barriers. Safety barriers, I have already mentioned, are an important protection tool, but when looking at what we expect in the case of a flood or an earthquake, we definitely expect that most of them may be affected or impaired or damaged by the event. These are the results of an expert survey. So if you note the bow tie approach, the safety barriers are the elements protecting us from the critical event and from its final consequences. This is what we expect to have, but this is what we really would have in the case of a natural event, with only few barriers still effective. And so this can result in a relevant change in the risk, where you can see that the depleted safety barriers cause a relevant increase of the risk with respect to what you expect with the normal safety barriers. One last word, this also applies, and this is a recent result we obtained still by an expert survey, to security elements that we expect to be damaged or no more operating properly during floods or intense wind, for example. And this may result in a specific type of technological scenarios that are natural hazard influenced security scenarios. So coming to a conclusion, and I apologize if I was a bit quick on the issue, but we have to end at 6 o'clock. My conclusions are that cascading events can be considered as atypical when looking at the conventional framework of risk management. And one of the kind scenarios, because the expected frequency of occurrence is low or the time of return is high. Still, they now represent a relevant threat for the energy and chemical industry. And we definitely need to improve our procedures for the identification, for the risk assessment, for the analysis of the safety barriers that we can use to protect ourselves from this type of events. And to include this in new approach to the design and management of the exceedance risk and in the resilience modeling. Okay, that's all for my presentation. Thank you for attending.
Thank you for this short and very sum up presentation, which point out the specificity of the cascading effects, and which draw some avenue for solving this kind of risk. I propose that we keep the question for the end after the second presentation, and I propose to Dina, and I will introduce Dina briefly before you give your talk. So I'm very glad to introduce Dina Daleya. You are a full professor of structural engineering And I think you are co-director of the Epicenter Research Center of UCL.
Yes.
You are specialized in disaster risk reduction and resilient engineering. Your research focuses on assessing and strengthening buildings and infrastructure exposed to natural hazards such as earthquakes, floods, and climate-related risk. Your work integrates engineering, data analysis, and innovative tools, including AI, to improve infrastructure resilience and continuity of also education system. Yeah. That's an important question for you. You hold the UNESCO chair in disaster risk reduction and resilience engineering, promoting safer and more resilient school infrastructure worldwide. That's very important things. And you also serve in leadership roles, such as director of the International Association for Earthquake Engineering. So, past, in the past, but that's important also. So I give you the floor for this second key.
Thank you very much. Thank you very much, Didier, for this very nice introduction, and thank you to Valerio for having introduced some of the concepts that I'm going to get over with this lecture, so hopefully I will be quick enough. So my talk is about resilience rather than risk reductions, or resilience as an essential element of risk reductions, and I want to start by providing a very early definition of resilience as proposed by Bruno et al. In 2003. Okay, thank you. And visualized here by Bocchini, and I've used this visualization because it's an interesting correlations that they were trying to make between resilience and sustainability, which will be a part of my discussion this afternoon. So according to Bruno, the well-known definition of community resilience, or system resilience, stands on the 4 dimensions of technical, organizational, social, and economic aspects, and on the 4 fundamental properties of robustness, rapidity, and redundancy, which are usually represented in these conventional ways, and substantially more resilience returns into more reliability, lower consequences, and faster recovery. So as you can see, taking up where Valerio left. So just to go through this, let's talk about urban resilience or community. I would like to propose this definition by Professor Fang at Tsinghua University, which looks at urban resilience as a 3-level space where the human activities, the natural and built environment, and the digital mapping are coexisting in order for us to really understand what is going on. And indeed, we can think about building and infrastructures as the foundation for urban resilience, and they are closely linked to the people daily work and life, integrating with society to become a highly complex megasystem, which can be somehow represented in this way, with the human different level of needs from essential to recreational, and these are delivered through a number of systems, infrastructures, and each of them are, let's say, can be described through some digital interpretation, so making this a mega system or a system of systems. My take on this is that we are missing something here, and particularly we are missing the foundations, i.e. nature. Nature and all the natural resources that allow this system of systems to actually work. And as you can see, while the arrows go around in the first parts, for the time being, we look for much of, let's say, until the end of the 20th century, we have mainly seen nature as feeding into the human system rather than necessarily the other way around. Where is resilience to natural hazards here? When we think about nature, we rarely think about the fact that there are natural hazards, and we define a natural hazard in relation to the fact that events that are, or let's say, natural aspects that are usually normal, or we consider normal, if we cannot control them, then become natural hazards. I.e., a nice breeze is very welcome, but then if it becomes a windstorm, then we call it an hazard. So with that perspective, it's very important to have a human-centric structural model here, but again, we cannot forget these interactions. And if we want humans to continue functioning, if we want to satisfy their needs, then we also need to concentrate on the sustainability aspects of these equations, i.e., when we talk about needs, we cannot talk only about the needs of this generation, but we need to talk about the needs of the future generation, and therefore today's resilience needs to be also sustainable. I'm now going to introduce, a way, let's say, an engineering way of looking at this. So here we are with a system that can be a building or a piece of infrastructure, so a more complex systems, which I might define, which has a certain life cycle, deteriorating with time, as all systems do, aging. At one point, before a disastrous event, we decide to intervene, and we can intervene in different way, or we can do nothing. We can, let's say, do some strengthening or retrofitting, or we can be smarter and do that strengthening or retrofitting in a more effective way. That then results in three possible scenarios after the events. In one case, probably if we have done nothing, the system will be damaged sufficiently that the only option is demolition. Or we can look at it and think, well, I did something beforehand, I more or less kept it going here. I don't know if you can see my pointer. Not, it doesn't matter. So if you look at the green line, clearly I have a quite substantial drop in capacity and functions, but I can eventually recover to probably a level that is lower than where I was acting before, but it can still functions. Or I can, if I've been smart, then I will have increased my resilience, and I will have increased my robustness so that the dip in the curve, in the red curve, is relatively small. This means that I have a relatively small functional loss, and that my system can also recover quickly in time, as you can see along the horizontal axis. So, very good. Of course, everybody would go for the red line there, because it's the one that gives us the least consequences and the minimum loss of functions. But the problem is, how much is this going to cost us, and is it a good investment? we can see here that probably, yes, it is a good investment, because although I can identify that at the time when I do the interventions, I'm going to spend more with the red line than the green line or the black line, and therefore in, let's say, a budget sheet or a balance sheet, I am in the negative there. In doing that type of intervention, I'm actually adding value to to my asset or my, let's say, piece of infrastructures, and therefore, during and later, I'm going to lose less value, or I'm going to maintain that value. This can be read in terms of economic value, or it can be read in terms of cultural value, if we are looking at an historic buildings, for instance, as we were discussing earlier with Philippe. And so it's worth thinking in these terms, looking at the traditional engineering approach, but also looking at other cultural or economic approach, or this could also be social, a way of reading some social variable. The advantages of resilience-oriented strengthening are well illustrated, for instance, by this sustainability life cycle proposed by Marini et al., whereby seismic strengthening is coupled with energy retrofitting, accounting for sustainable material and processes, and this create a fast virtuous cycles where life is extended, hence embodied energy loss is delayed, and material are recycled and or reused, and both resilience and sustainability are delivered with the same type of intervention. A second virtuous cycles is proposed here by Micheli et al., and it's more related to organizational structures, where the relationship is established between resilience, sustainability, and digitalization. So we are going back to a certain extent to my first slide. The model shows that, as you can see here, the interdependence between between sustainability and resilience stands into the fact that they both have 3 dimensions which relate to the environment, the economy, and the society. And while the sustainability work on the resource efficiency, the impact reduction, and the transparency, the resilience is the other side of the coin that works on absorption, adaptation, and flexibility and short-term outlook. Now, if we want to look at the long-term outlook, then we need to get into the what is called agility for organization, but this again can apply to community or can apply to other dimensions, and the ability to transform and renew, and the ability to use digitalization, such as artificial intelligence or the let's say, 4th industrial revolutions, and that exploitation in order to better understand the relationship between sustainability and resilience, and ensure that these are called upon when they are needed. So, given this general framework, I would just like to show you an example of where we have tried to apply some of these concepts, working with some advanced, let's say, computing capacity, if not artificial intelligence, and working directly, at the same time, working directly with community, trying to improve the educational resilience in Cagayan de Oro in the Philippines, and more widely in their educational system. So here we started by characterizing and minimizing education disruptions to seismic and flood exposures and defining their vulnerability. We then went to trying to develop an affordable and accessible decision-making support tool and capacity building, and we deliver some capacity building workshops, and I will discuss this in a minute. Finally, integrating physical and social vulnerability to better quantify post-disaster education continuity. And in the more recent future, we will go on to expand this to extending from local to regional model that are going to be co-developed with open source risk communication and decision support system for the island of Mindanao, which is the southern island of the Philippines and the largest in the country. So in terms of the work that we did, the first step was to characterize the structural vulnerability of the infrastructures, both to seismic and flooding systems. In this particular case, we used the glossy framework, which we had developed previously with the World Bank, which it allows to define taxonomies for buildings and therefore to identify typologies, and then given the typological distribution, allows us to identify specific fragility behavior given a typical structural type. Some of the discussion this afternoon already touched on the fact that this is a procedure that is very well established for within the sphere of seismic engineering. So we try to expand that to flood engineering, where there are less analytical resources in this aspect. Likely for the Philippines, they have a very good system of hazards map for flooding at national level, which gives return depth, qualitative range of depth for a given return period, so useful at least to start with. We intersect this with, again, a taxonomical system and a way of identifying vulnerable element which allow us, if not computing vulnerability from an analytical point of view, but at least provide empirical curves which allow us to define what are the different vulnerability for the different school compounds in that cities, and therefore at first discriminant, and then we also can compute what would be the repair cost for the different horizons given the water depth. But in terms of defining educational resilience, it's not sufficient to look at the building and look at how they will be damaged or lost functionalities. We also need to get the community to go to the school in the aftermath of the event. So the road network, and particularly the bridges, becomes quite important elements. So again, similarly, we look at the bridges and the way they can model, but also the road network around the schools, and we determine the fragility. This is the seismic fragility, but also the flood fragility that they will experience. Now, how are we going to put this together with the idea of having an affordable and accessible system of reliability? So the idea is that we can basically provide these resources as the base of a very simplified platform where we introduce these into a Bayesian description of the system, where we start with the hazards and we understand what are the consequences for the individual elements, and then for the survival or failure of the system, where here the system are the schools and the community around the schools. The element is becomes accessible and affordable because instead of doing it in our office, we are going to the community and we are developing these tools with them by going in two ways, by using field trips to the various schools to understand the vulnerability and to derive the vulnerability, but also then doing hands-on tutorial for them really to learn how to use the Bayesian network and the programming, the Python programming, to introduce their own capacity. So this we can say that we have been successful in doing this, but in fact, we went through a series of evaluations to make sure that actually there is some benefit in organizing these activities. And these are some of the feedback that we received. And it was interesting that some of the end user thought that maybe we were not very technically rigorous and that we could have done better. But on the other hand, in most cases, the result was that there have been an uptake and a better understanding of fundamental concepts from risk, vulnerability, and exposures to system reliability, thanks to the process that we went through. So, however, in order to understand really what are the consequences of this particular scenario that we were looking at, it becomes important to really understand what are the social vulnerability that the different community are related to. So, how did we go through this? We have the detailed system reliability analysis using the Bayesian network to treat a school complex as a system of multiple buildings. We do the structures learning of the Bayesian network parameters by using fragility data school buildings, as we have seen, and then we use matrix-based Bayesian network. This reduce the dimensions of the problem. On the other end, we use probabilistic model for assessing shelter needs that are influenced by social vulnerability status. In this particular case, we used 4 indicators: the type of settlement, the economic status, the housing quality, and the presence of dependent. And we used these 4 because they were in their census, so we could use this for each of the neighborhoods as aggregated proportions. Then we integrate this in the Bayesian network framework for equity, focused evidence-based decision support. So we investigate the unequal distribution of education risk through spatial mapping, quantifying the relative importance of vulnerability factor on education continuity and computing efficacy of potential policies. So this is our, again, the detailed Bayesian network, and now we sort of reduce it by the branch and bound algorithm that you can see in the publication with Jung Byung et al. But the thing that is interesting here is that we used a Delphi survey, which is a typical, let's say, social sciences approach to determine the shelter needs rather than just on the basis of the outcome of the census, by interrogating the expert in, or the, let's say, actor and stakeholders in the different local authority on what did they think that the combination of the 4 different attributes that I mentioned earlier would result in terms of shelter needs. And we can see with this approach that, first of all, schools are clearly different education continuity problem. and here they are listed from long-term to short-term availability or non-availability. But more importantly, that there is a substantial difference in what it is expected as disruption when we don't consider, or we consider, the Delphi analysis. So the local perceptions are fundamental to change the statistical or the statistics of that would be obtaining just from the census statistics. And so the higher probability of long-term disruptions were accounting for shelter needs associated with social factors, because the schools are used for shelters. So it's not just the fact that they might be affected by a flood or a seismic event, is the fact that if they survive that flood or seismic event, they're then going to be used as shelter, and therefore they cannot be used for education. And therefore you need to find alternative to keep children educated during that period. So here we can also see, as I said, that there are different level of differences, and that the factors differs for the different schools, because there are a different distribution of these 4 indicators in this particular area. And therefore this one goes toward the sensitivity to different policy decisions. So then we can look at the use of AI for integration of this physical and social vulnerability to design holistic resilience tools for community with a focus on education infrastructures. So in this case, the disaster preparedness and resilience, in terms of that, we can use satellite imagery-based typology and vulnerability assessment for prioritization of interventions. We can use AI for mapping social vulnerability according to for instance, using the UNDP digital social vulnerability indicators. And we can use also chatbots for integration and personalization of technological tools for community-led disaster preparedness and capacity building. So some of the things that we have done through the workshop can be done remotely by letting people to use a chatbot facility in order to define what are their particular take on the relevance of importance, for instance. And then we can still trace the recovery. So some of the tools that we will be using are, for instance, using spatial analysis of school, using building footprints, but also looking at this decision-making framework directly working with the communities, as I said before. And because we are very short of time, here we are with the conclusions. So resilience needs to be sustainable, and sustainability needs to be built on resilience. The digital dimensions may be instrumental in facilitating the communication and provide, in a short period of time and with modest resources, evidence that can be used to support decisions. It is critical for resilience studies, I think, to include the social aspects of response to disastrous events. And as we have seen with this particular case, the local knowledge is fundamental to the realistic modeling, and therefore to how then this can influence decision making. The science behind resilience analysis can be communicated and transferred to operators with relatively simple approaches, giving them the possibility of co-designing and effectively use decision support system. And this is because they are at the far front of the problem. So although they might use a different language and they might not be familiar with the specific techniques, once you describe the logic behind something like the Bayesian network, they promptly get it. The affordability is delivered by empowering the stakeholders to create scenarios of interventions that are also commensurate to the local resources and really determine how to use those in the most effective way. The escalation of risk due to climate change this is a more general consideration, is a global problem that requires the involvement and response of all nations and community worldwide, and therefore we need to work together in a respectful way to find effective and implementable mitigation action. It's great that you have such a large project here in France, but it's very important to understand how then we work with other community in order to make sure that we control the consequence of the climate change, let's say. Thank you very much. And this
We have time for questions. I think we can 10 minutes, maybe. 10 minutes for some questions for the two speakers. Start.
Jean-Marc Tacnet in RAE. Thank you to the speakers. Question for both of you, in fact. What is the biggest remaining challenge for cascading risk and resilience assessment? And what is the most important for you? Improving knowledge about physical vulnerability or scenario identification?
Interesting question. What is the most important element? For me, the most from a purely theoretical point of view, it's the ability to string together the whole process and to get to scenarios or to consequences that make sense and are realistic, and to be able to compute the uncertainty or the alias, as you call it, in each of the steps, and to be cognizant of the uncertainty. To me, that's the most important way. So, for instance, in some of the work that we do, we try to bring together Bayesian network with agent-based modeling, because the Bayesian networks allows us to provide a full probabilistic approach, and then the agent-based allows you to explore many different alternative scenarios. But they still have their limits. So yes, that to me it's from let's say purely research and analytical point of view.
Well, maybe on my side I can highlight two points. A first one concerns the multi-scale and multi-level nature of the problem. You need to carry out a systemic assessment, but this should be informed by models that have a progressively increasing granularity. And this is difficult. It's difficult to have these models. It's difficult to have models addressing all the single points of the problem. It's difficult to put them together, to have them considering the appropriate interactions, and to provide results going from the bottom up to the high-level assessment. There is also, however, another element that I think is even more important, and it's not a technical element. That's awareness. I mean that we can only improve if we are really convinced that we need to work on this problem. And I have assisted several times in discussions with industry managers or with regulators that when presenting these problems were not really convinced about the importance of devoting resources to this type of assessment. And awareness is the first starting point for solving even complex technical problems, from my point of view.
Totally agree.
Hi, thank you very much for both of your talks. It was something that I'd be very curious to know more about is that both of you work with sectors that can be also considered risky in themselves. If we're thinking about chemical and energy industry or AI, those are technologies that in their normal functioning without external events might present risk for people elsewhere. Because of the extractive logics on which they rely. And I'm wondering how and if those kind of questions find a way in your research. Yeah, is my question. Thank you very much.
I'm not sure I've properly got your point in the questions in the question. So it's not easy to identify exactly which is the main relevant item to focus on in research, and so this might require might be dependent on the specific problem that you are facing. So this can be maybe further discussed.
Thank you. Well, yes, it is true that when we use particular tools, we need to think what are the consequences of using these tools. I think that's where you were aiming at, and certainly AI has a lot of possible unintended consequences depending on how we use it. In our work, we try to use as much as possible explainable AI, so and we try to do as much validations and of the results that we get with different methods that are more that are based on our knowledge. But of course, there is always the possibility that then these tools are let's say, also misused. So we were referring earlier to this, to the possibility of leaving of producing this programming platform that then can be left to the end user to play with. I think that to a certain extent we also need to rely on the motivation and the ethical centered of the end users, which at least when we work with this community, they are very, they really want the extra possibility of doing more than they are doing with the tools that they have. So I think that they are conscientious and yes, properly used for the better of their communities. Yeah. I don't know if this answers your question.
More questions? No? No more questions? Maybe I have a question about the need for advanced modeling. What you think? Because when you use Bayesian network, in some sense, you use some simplification. You introduce probabilisticity in some sense. What is the place of advanced modeling of, for instance, floods? Or what is your opinion on the use of complex models to produce knowledge and decision making? What is your? Do you need, in fact, more data than models, or this is something you have to mix together to get your assessment?
Well, if I can give a first answer to this, I mean, it's difficult to frame. This is a problem that is difficult to frame. Definitely, the more data you have, qualified data you have, this is another issue, the point of the accuracy of the data that you have, because it's not automatic that if you have more data, you can obtain a more accurate answer. But in principle, if you have more data having all the same level of accuracy, you would be able to have a higher precision in the solution of the problem. However, as an engineer, there is a level above which adding further data doesn't add a relevant precision to the solution. So the problem is, which is this level that you want to achieve? This is a point. The other point, however, that is always there is that in risk assessment, it has been a conclusion since at least 1 decade and even more, that you always need to associate an uncertainty analysis to the results that you produce. Without it, without a clear understanding of uncertainties, there is a clear risk of coming to, let's say, not wrong decisions, but at least to having a wrong feeling that you have taken decision based on clear evidence, which actually might not be so clear.
Yes, I think that the issue of confidence that you are hinting to is fundamental. To me, the first step is that as engineers or as we have been trained to use model as representation of reality. So in that respect, we need to be sure that we are using the correct model first. That the modeling that we are doing, it's a good representation of reality. Then it can be simple or it can be more complex. I can add a certain number of layers of variables or non-linearities, many things. But first of all, I need to have sufficient understanding that the model that I'm using is a good representation or a reasonable representation of reality. Data, it's always welcome. As Valerio was saying, that doesn't mean that it's good data. So, there is good data and there is bad data. But also, it's something that we also learn, for instance, from working on existing building or existing infrastructures. Sometimes it's not the number that gives you the information that you need, but it's the qualitative assessment. And in that respect, the information that can come from the social sciences sometimes is more important than the physical model that you are using to describe a certain phenomenon. I think that's a very important piece of thinking that we need to do as engineers.
Okay. Oh, thank you very much for your very interesting keynotes and stimulating keynotes also for us. Huh? Comment? Alors demain matin, on reprend à 9h. Hein, et donc ce soir, le bus, c'est 18h30. Maintenant, il faut... Donc ceux qui participent au dîner de ce soir doivent se rendre au bus qui nous attendent à la sortie. Voilà. À demain matin, donc.